Let's see how that would play out in a real-life situation. Okay, let's say we have a patient that, now I'm going to use CT for example because we have a patient that comes in and they have a subdural hematoma. They hit their head, and if we were to look at the numbers that represent flowing blood in the head and coagulated blood in the head, we would find that, let's say for example, that coagulated blood has a CT number of, I'm just going to give some arbitrary numbers out here. Let's say that it has a CT number of 100. Okay, flowing blood has a CT number of 95. Okay, so there's only a 5% difference between them as far as their characteristics. Patient comes in and he goes to nuclear medicine tech who graduated from that other school that we won't mention. That technologist does the CT scan, but because they want to save time and they want to not damage their equipment, they use less radiation. So they go 100 counts. Okay? With the 10% error, this error is greater than the difference between these two numbers here. Okay, this is my 5% difference. Okay, this 10% error, because it's greater, is not going to show the difference between those two structures. Does that make sense? So I'm going to tell that patient, hey buddy, you know, I don't know why you came in here, you're wasting your time, go on home. And that guy is going to go, thank you very much, I guess maybe there's nothing wrong with me after all. So he's going to go home, right? But realizing that there's a problem, he decides he's going to go to one of you who knows that we need to give more radiation to reduce that amount of error created by random. Okay? So, now that we use more radiation and we have a 1% difference, if my 1% difference is greater, I mean it's less than the difference between the two objects, it's going to stick out like a sore thumb. And we're going to say, oh my God, we got to rush you to surgery right now. We're going to drill a hole in your head and we're going to drain out that subdural hematoma. Okay? So, there's a very important reason why you guys go for a certain number of counts. Okay? And later on we're going to be talking about how many counts you need. We actually have a formula that we use to do that. And in fact, we have what we call levels of confidence, or confidence intervals. I don't know if you've ever... Who's had statistics? No? Okay, well basically what we do is this. Okay, let's say that you took 10,000 counts. Okay, if we have what we call one standard deviation, if I take the square root of 10,000 counts, now I know that if I had a source of radiation and I counted at one time, I got 10,000 counts in 1 minute. What would happen if I counted it again? Would I get the same 10,000 counts? What? Yeah, I should. Would you bet your life on it? Would you bet Monica's life on it?
Yes.
Yeah, Monica's life.
No, okay. Your chances of getting that same number again are like you have better odds winning the lottery than getting that same number again. If you got the same number over and over and over and over again, if you got 10,000, 10,000, 10,000, 10,000, that means there's something wrong with your equipment. And in fact, I'm sorry, Ashley, did you say something?
No, I was just laughing because it probably has happened, but they didn't know something wrong with their equipment.
Exactly. This is why, you know, we actually have a test to prove that your equipment is detecting radiation randomly. It's called the chi-square test. You're supposed to do that periodically, but let me give you an idea of what we're talking about here. Okay, so if I take the square root of 10,000, you know, then what I wind up with is 10,000 counts plus or minus 100. Okay? So that means I've got 10,100 and 9,900. Okay, this is a range. And statistically speaking, if I was to count the source of radiation 100 times, I would expect to find that 68 out of 100 counts or 100 observations would be within this range. Does that make sense? So this is what we call one standard deviation, or this is what we call the 68% confidence interval. I am 68% confident that if I did spend the time and count that it would be within this range. Huh?
Second deviation, that 97?
Ooh, nope. Close. 95. Okay, this is what we use in nuclear medicine. Okay? If I take the square root of 10,000 again, this time I'm going to multiply it by the number of standard deviations. So now if I have 10,000 plus or minus 200, so 10,200 to 9,800, okay, that increases. Now, it's not necessarily accurate, but it is, it just means that I would be getting reproducible results. In other words, I would be within this range 95 out of 100 times. Okay? And that's what we call the 95% or the 2 standard deviation confidence interval. Okay? The third is 99. The third standard deviation, okay, again, it's the square root of 10,000. So it's 10,300 to 9,700. You can expect that 99% of the time. Up. Okay? In nuclear medicine, you're going to see that we normally use this for most of our imaging procedures. The only time we go to 3 standard deviations is when we do uniformity correction for our SPECT camera. Okay? On a daily basis, you typically collect about 3 million to 5 million counts. Okay, that's a 95% confidence interval. Okay? And the number of counts that you collect depends upon the matrix that you use to accumulate your uniformity. So if you use a 64 by 64, all you need is about 4 to 5 million counts. And that puts 10,000 counts in each pixel. Okay? Because later on you're going to find that we have another formula that we use to calculate how many counts you need for a certain standard deviation. But before we do that, let's kind of talk a little bit about this handout here, because you probably heard these terms before, and I know that it took me a long time before I ever considered statistics something important. Until I got into nuclear medicine, I could have cared less about statistics. But the first thing I wanted to discuss are measures of central tendency. This one here you're probably very familiar with. Okay, the mean. You basically take, like let's say that you worked 5 days. Okay, you add all of those up, divide it by the number of days that you work. It tells you that on an average you get $200 a day. You've all done that before. Okay? Some examples that you guys, write this down, page 58 of your math book. There are some examples of mean, median, and mode. Okay, now, what does the median mean? Okay, I gave an example here of a situation when you have extreme numbers. Okay, it says it's the middle value when the numbers are arranged from increasing or decreasing order. So in other words, you set them up from the lowest to the highest, or the highest to the lowest, and you find the middle value. So there's 1, 2, 3, 4, 5 observations. We find the middle one. So 150 is the median. Does that make sense? So it's just the middle value. And we normally use that in situations where we have extremes. So I put down here that it's used, yeah. Oh, and also here, okay, so if you have an odd number of things, it's usually pretty easy to find the median. Because here I had 5, so that means the middle one is, there's 2 before it, and there's 2 after it, so it's right in the middle. When you have an even number, then you add the 2 in the middle together and then divide it by 2. You see what I did here? So here I've got 6 readings, so 1, 2, 3, 4, 5, 6. So when you have an even number, you take the 2 middle values, add them together, and divide it by 2 to get the median. Okay? But this is why we use that. Because like I said, okay, you got these people working in your company, and so you've got the manager who makes $1 million, and you got the clerk makes $20,000. So when you add all those together, the average salary is not $275,000 per person, is it? No. So you can see how that would be misleading. Okay. But when you take the median value, okay, so the median value is more realistic. We have we have 1, 2, 3, 4 observations. We add the 50 and the 30,000 together, divided by 2. So it's a more realistic value when you have extreme observations. Okay. So when you guys are making $1 million a week, think of me. Okay. Yes. Now, this last one that I listed here, the mode, this is just a number that repeats itself. And that's why I said here, okay, the value that is most often repeated in the set of numbers, and then the example above, the 350 appears a couple of times, so that would be the mode. Okay? Now, normally when you're dealing with randomness, you should not have numbers that are the same. They'll be close to each other, but they won't be the same. So, if you have a perfectly random system, okay, the mean, the median, and the mode should all be equal to each other. And then you get what they call the, what do you call that curve?
Bell curve.